We have about 10 minutes left. If you guys have any specific questions you want me to look at, I'm happy to do that. Otherwise, I think I'll let you go. Like I said, I'm willing to sit here and talk about anything in particular. Somewhere over here, I have the exam from spring 2017 that we could go over if we wanted. What's up? We have a question coming on? Maybe I left that upstairs.
I have a question.
Sure, please.
Yeah, so this has something to do with exam 3 and
Okay.
how you said basically we're going to get one example output and the rest is going to be like other tests.
I said
Like
you'd you'd have some example output and then some hidden tests that you wouldn't know the answers to. Yeah.
Yeah, hidden tests.
Yep.
Yeah, I just had a question because like on the last homework for homework 7, part 2, for the movie list one.
Yep.
So I think like we all handed it in. It's okay to talk about it now. So for my program, basically I had like an if check. Basically, it would check like, okay, is this movie larger than the min year and shorter than the max year? So like greater than or less than signs
Yeah.
as an if, and then it would do the code. So if it passed that, it would do the code. And that worked for the example outputs we were given
Mm-hmm.
in the file. So, you know, that like we were given those example outputs. I'm like, okay, this code works. I submitted it. Submitting gives it things that I couldn't account for on the example problem.
Mm-hmm.
Like, what if the movie that got the highest rating was on the exact min year or exact max year? I didn't know to account for that because the test output didn't like worked for what I had.
So that's a really good point. And you know the answer is we give you examples to demonstrate the behavior, but that's not a substitute for thorough testing. You know, and that's part of what we want you to do in this, right? If it were a paper and pencil test, which most of these were in the past, we would be looking for those types of errors, and we would ping you on them. You would lose points, and now, you know, you're losing points on the homework because
no, I didn't lose points. I fixed it. Like,
but you know that's you know, so that's the idea is you and we will try to give you a decent sampling of output, but you know we will definitely use different output. You should be checking error cases. You should look at how we want you to handle bad input. Right, those are things, you know, we've been kind of telling you about these going, you know, as we've gone through. This is part of what you need to be learning, and that's one of the things that the hidden cases allow us to test is, are you able to test your own code, you know, when you don't have the crutch of submitting, you know, telling you what all the right answers are.
yeah, that was just like my question because how would I know I was supposed to account for that when the test examples fit within what I already wrote?
Well, because it's written in the PDF. I mean, the PDF says inclusive or including those years, something like that. I don't remember exactly what the phrasing was, but that's one of the things that, you know, if you look at the, we had a lab on testing and debugging DocX. You know, we asked you to come up with test cases, and one of the things you were supposed to be looking at was, you know, you want to test the boundaries. You want to test things at the boundaries. You want to, I mean, that's part of the testing is you have to come up with test cases that test your code against nominal failure cases. You test in the middle, you test outside, and then you test on the boundary.
Yeah, I'm just worried that like the example.
I know, but it's not. I mean, that's not something we can handle. I mean, we can't give you all of the answers. Otherwise, we're not testing it, right?
Well, they're not the answers because I still have to write the code.
Well, but it's in the spec. And you know, we if we make a mistake, and we'll recognize that. But you know, if it's in the spec, you know, you're expected to test it. You know, I that's part of the you know, part of testing your code is going beyond, particularly with these hidden tests. You've had the crutch of not having to do that. but you haven't been in a test situation. So as part of being in a test situation, make sure your code works for all the cases that are, for things at the boundaries.
Okay.
I mean, that, I'm sorry, there's not really another answer. Yes, it's tough. That's,
Yeah.
stuff, that's that's part of the job. All right. No lecture exercises today. These, you should have done the lecture exercises. I'm just looking at questions pop up, so this is not related to anything you asked. But no lecture exercises today. Okay, any other questions? Any material that you guys want me to go over?
Will this code be on the website submitting?
Should already be there.
Oh, okay. Just making sure.
It's up in it's in the on. Hold on. It's in the I'll show you if I can find it. There we go. So if you go to if you go to our web page, right, you can get there from Submiti. You can get there typing this in directly, and you go to code written in class.
Oh, okay. Thanks.
Right. That's where we've been posting. We've posted a lot of code there over the semester, but there's exactly the code that we just ran. All right, including the run in the testing code. Okay. Any other questions? Any questions about material? If not, it is 3:48. Okay, go ahead, please.
I'm still really confused about how it only takes 8 comparisons for that third line. Because I get the lists are sorted, but would you still have to compare each element to each element in the other list in order to know exactly where it places in the combined list?
For the merge?
For the merge sort.
Okay, so if you look at the merge algorithm itself, let's pull that up. Now, I'll pull it up here. Right, if you look at the merge algorithm itself, right, so this is just one line, right? Right, that's where the merge is being done. Right, so the output of this is a sorted list. Right?
Yeah.
Okay, so we're going to accept that when we get to this point, new list is sorted.
Yeah.
Right, so we're going to give new list 2 lists. These lists are both sorted.
Yeah.
Right? So when we come in here, actually let me move over to here. If you don't have a question, I'm going to stick here until until either the questions are done or I'm worn out, 15, 20 minutes max. But in the meantime, I'm going to go over this stuff. If you're done, you guys can be done. You don't have to stick around. So let me walk through the merge algorithm again. All right. So if we have a merge algorithm, right, and I'm going to just do 2 sorted lists. It's really a beautiful, simple, beautifully simple algorithm, which is really kind of cool. These are the types of algorithms that I love because they don't necessarily make sense when you first think about them, but as you go through, they make more and more sense. So we have 2 lists, L1 and L2. Now our preconditions, the stuff that has to be true when we come in, is these 2 have to already be sorted. So we get down. So you're talking about the place when we have 2 lists of length 4, for example.
Yeah.
So we'll have 1, 3, 9, 12, and L2 would be, I don't know, let's say 2, 7, 8, 15. Okay? So they're both sorted. So what we're going to do is we're going to set up. Let's do this pictorially, right? So 2, 7, 8, 15. I'm going to leave myself some room. Okay, so we come in here and we have 1, 3, 9, 12, 2, 7, 8, 15. And we set up these two indices, I0, and I0 is equal to 0. It refers to the first element. I'm sorry, that should be I1. Let's keep our subscripts the same. I1 refers to the first element in list 1, and it's going to start out at 0. So it's going to start out pointing at this 1, right?
Yeah.
And I2 is going to be the same thing. It's going to start out being 0. It's going to refer to the first element in list L2.
Mm-hmm.
So until we get one of these to the end of the list, so we're going to be in a little while loop. Until we run out of elements in one of our lists, what we're going to do is we're going to look at the first element in L1, and the first element in I2, and we'll have this new list, right? New list. It'll start out blank. And if this is smaller than this, we'll append this. If this is smaller than this, we'll append this. And notice that these both are sorted. So this is the smallest element in L2. So by making one comparison, we can determine if this is smaller than everything in this list. We already know it's smaller than everything in our own list because our own list is sorted. So by making one comparison, we can determine that this is the smallest one left, right? So then the
Yeah, I think I just figured out why I was thinking of this wrong. I forgot about the brand new list.
Yeah. But isn't that beautiful? Because you're making one comparison, but you're actually making, well, one.
Yeah,
two, three,
it is
four,
pretty
five.
genius.
Yes, you're actually making 7 comparisons with this one comparison, and that's where the genius of this comes in.
Yeah.
I did not invent this routine.
How old is this? Must be pretty old. I mean.
Yeah, it's 60s, early 70s.
Okay.
So I think it may be older than that.
What is it? One more question.
Sure. Yep.
So in a say a search function where you're what is it? It's two for loops, and the second for loop only compares the first indice with everything in front of it, right?
Mm-hmm.
So something like we had in the last lab. That's
Okay.
O(n) squared, right?
If you have to do it n times, yeah.
But you're not doing it n times per indice.
Right.
You're doing it like incrementally less,
Right.
one less. So is it still O squared? O(n)
Yeah,
squared?
and that's the horror of the n squared trap. So what you're saying is, you have this list. I'll just put some x's in there to represent values.
Yeah.
Right. I don't even know how many I put in. And you're saying you do this, right? So the first guy has to be compared to everybody else. So if the list is length 1, the first guy does n minus 1 operations, right?
Yeah.
And then the second one can do n minus 2 operations, right? Because it only has to go, it can skip this first one, right? But it has to do all of these, right?
Yeah.
So the second one can do n minus 2 operations. And the third, and we should probably put the subscripts down here, right? And we get all the way, and the next one, x sub 3 has to do n minus 3 operations, right? And then we get all the way down to x sub n does 0 operations, right?
Yeah, but it's still O of n squared.
Right. Well, there's n of these, right?
Yeah.
So you have to do an operation for all of these. And now let's figure out what the average number of operations is. Well, this is a sequence, right? This is 0 plus 1 plus 2 plus n minus 1. Right? So this is a summation I equals So we can do this as, I equals 1 to n minus
Yeah.
1, or 0 to n minus 1. I guess we would have to do and you of I, right? So you can work out that summation, and that summation is n times n minus 1 over 2, something like that. Or you can just look at, we have n iterations here. The average iteration, right? If we take since they're all going up by 1, n minus 1 plus 0 over 2, right? N minus 2 plus 1 over 2. They all average out to be n minus 1 right, divided by 2 is the average number of iterations, is the average, if you pair this guy,
the average number of comparisons.
The average number of comparisons per, and we have to do that n times. So it's again n squared minus.
Okay.
Okay. So
I think I understand it.
So yeah, so it's a so you can either do it as a summation and solve the summation, or you can figure out the average number of comparisons, and then multiply by
proportional. It's proportional to n squared.
Right. Either way, it comes out proportional to n squared.
Okay.
Okay.
Got it.
Which is a pain in
Thanks.
the neck. It's
I have a question on this.
It's unbelievable sometimes. All right. Anything else?
Yeah, I had a question on this exact one as well.
Okay.
So would it be n squared minus n over 2? Or is it just n squared minus 1 over 2?
Yeah, it would be n squared minus. Well, the average is n minus 1 over 2.
Okay.
So the average number of comparisons is n minus 1 over 2. The order of the algorithm is n. Right, we'd have to do that n times that average value. So that would be, order of n squared minus n over 2. But then we drop off the multiplier, the 1/2, right? And then we also drop off all lower order terms, so it just comes out as order of n squared. Okay?
Got it. All right. Yeah, I had a question on that same one, but thank you.
Oh, awesome. Yeah, you're welcome.
Oh yes, another question on the binary search.
Go ahead.
So then, when you how you keep going halfway until you meet what the value should be or whether the value is there.
Yeah.
In the case where it's like an odd number starting, for example, if you have a list of length of 7, you move 1 up to the 4 or you move 1 down to the 3.
It depends how the algorithm was written. The way the one we gave you in the book is written is it always takes the midpoint. So if you have a list, of length 5, for example, the midpoint would be 2 using an integer divide. So you would put the So, I don't remember.
That's fine. I could check the book.
Yeah, the key here is that it doesn't matter where you put it.
Okay.
But it has to match how you implement the algorithm. So I think we move the lowest up. So I think we put it on the upper half. But
okay. There's
a perfectly valid binary search that does it the other way. And I don't remember I'm not exactly sure which one we have implemented here. So I'm sorry. That's all the difference is.
So it has to just match the algorithm.
Right.
If you're going 2 down, then you have to match it with 1 up. Okay, I got it.
Yeah.
Thank you.
You're welcome. Anyone else? All right. Thank you. I think I'll shut down for now, and I'll get these notes up. Have a happy Thanksgiving. If nothing else, enjoy a little time off. I know I'm going to. And we will catch you again in a week with You think this was fun? Wait till we throw in recursion on this. Turns out merge sort is beautiful in recursion. It's very elegant. So we'll show you that. Talk to you guys later.